Good day, ladies and gentlemen. Welcome to the Al-Farabi Kazakh National University GIS Forum with SuperMap. This is Olga from SuperMap. It's very happy that Al-Farabi Kazakh National University has invited us to present in this webinar. And it's more than happy to have all of you here today to join with us for the exciting technology. Wish you can get what you are looking for from this event. Also, we are always open to any ideas and comments of yours that to help further discussion and cooperation with you. Now, let's go into the first presentation today. As we all know, normal 2D map is powerless in managing the complicated situation of model city. So 3D has become the best choice for building smart city system. However, if we use beam or fan model for all buildings in city will definitely increase the cost of work and budget. So a good solution is to build key buildings with beam or fan model, then generate the big regional city model with oblique photography. SuperMap has done lots of research and projects to improve oblique photography usage in smart city system. Unfortunately, Mr. Jason has encountered some personal issues today. So let's welcome Mr. Ismail, Technical Support Engineer of SuperMap, to provide the presentation 3D GIS, the foundation of smart city. Let's welcome Mr. Ismail.
That's good. Thank you, Olga. So good afternoon, everyone. Thank you for having me. In this session, actually, we will discuss about the SuperMap GIS capabilities for the creation and development of the smart cities. Okay, I will share my screen first. Okay, so hello everyone, good day and welcome to this SuperMap webinars. Before that, Olga already introduced me, but let me introduce myself. My name is Ismail Suryakusuma. I am Technical Support Engineer in SuperMap Software. So today, what I'm going to talk about is about the SuperMap Oblique Photography technology and its application in Smart City. So actually, what is oblique photography? The oblique photography, it can capture real world through the multiple sensor using flight platform as shown in these pictures. They have 5 lens of camera and it's commonly used. So there are many sensors that simultaneously collect images from different angles. Image capture from vertical ground, it's called the positive films, and the image capture from certain angle between lens and ground, it's called oblique films. So oblique photography technology is a high technology developed in the field of international surveying and mapping in these recent years. It overturns the previous limitation that orthophotos can only be shot from a vertical angle. By mounting multiple sensors on the same flight platform, it can also move from a vertical, capture image from 5 different angles, including 4 tilts, to quickly restore the real world. Next is from how to capture the data until automated modeling. These are some of mainstream automated modeling software applications that can produce oblique photography or 3D model data. This application can be connected with SuperMap GIS platform. It is included the Street Factory, Context Capture, Photoscan, Altizer, and Pix4D. So this is the workflow of automated modeling process of oblique photography from data acquisition to aerial triangle. Also, and then they converted into point cloud, TIN data, and then DSM data until it produces 3D modeling. In this video, this is one of example oblique photography implementations. It is located in the Shanghai city in China. This project completed in October 2016 by our institute using drone tail photography technology. The flying area is about 20 square kilometers. At this time, our unit used the drone and we have very good grasp of it. So we put the image into the resolution of 4 centimeters so that the modeling effect is very good and the accuracy is also high. It provides a real external environment for Shanghai City to directly plan and design road and underground pipe networks on the 3D dimensional model in the future. These are advantages of oblique photography modeling. The first one is high efficiency. It can collect a large 3D space area with different angle using flight platform. Second one is high realism. It means it has realistic 3D space scene resembling a real world. As example, it has prominent roof features, exterior wall, as well as fine features like terrain and landforms. Next one is the high accuracy. It means it has accurate geographic location and coordinate information of the features. And last one is the low production cost. Low production cost because it is using flight platform that can cover large area with large 3D space scene. So it needs a short time, low cost survey activity to get result. And the process of making oblique photography application as shown in these pictures. The first development of the oblique photography area platform, which mainly include the flying platform, such as the powered delta wings and aerial vehicle, and oblique photography cameras. And then there is oblique photography air flight that responsible for the implementation of the aerial flight to obtain oblique image data. After that, the processing of the oblique photography, which mainly include a fully automatic or manual intervention modeling based on the oblique images and the large scale of topographic data, surveying and mapping. After that, there is a 3D GIS platform that support oblique photography data. This platform provided by SuperMap. We could use GIS platform to do some analysis, some display to make applications. So finally, it based on the application development and oblique photography data and 3D GIS platform. Next is the challenges of oblique photography. The first challenges is how to deal the massive data. There are several ways. The first one is using the native rate of OSGB. OSGB is a common data format to store 3D model, and most mainstream 3D modeling application able to import and export the OSGB data format. Second, using fast dynamic loading. It means a full use of data native to a low level of details, instantaneous full load, high frame rate, less memory consumption. These are oblique photography modeling software applications. Each of these software has its own data format. So how to connect to this data format and integrate it in GIS platform. SuperMap provides a convenient ways and efficient model loading method by using a configuration file, mostly in XML files, to describe what data need to be loaded. And then the original model data called the OSGB, already mentioned, that is a common file that mostly 3D software modeling capable to export. So this is one of example data acquisitions. This is done by DGA UAV and DGA Z2 modeling software to quickly generate 3D model data in format S3m and then browse and display it on SuperMap GIS platform. This is another example how to load the massive data. So it has capability to show massive field and high-speed browsing of 3.2 terabytes of oblique photography data, and then render it in the web applications. As we know, photography data has large sets of data. Then how to support the management of large-scale oblique photography data? Let's find out how SuperMap manages large data. To optimize the performance, there are several ways to do it, such as the data generation slice, but not too small slice. It is recommended from 300 to 500 meters. It is recommended. The other one is do the texture compressions and then save in large files to reduce the system access to broken files. And then you can use MongoDB for easy copying and sharing, as MongoDB well known for its performance. And also the other ways. For example, in order to unify the coordinate system, the data is converted into the coordinate system. In order to improve the rendering performance, the data combined with root nodes and texture compression operations. These processing operations are very inefficient because each step of the processing operation for oblique photography data requires a large number of small OSGB files to be read, processed, and restored. In general, we will perform multiple processing operations on oblique photography data. So it will read and stored repeatedly. Multiple input and output greatly affect the processing efficiency. Then we can transfer this one by one processing step into processing operators. So what are the benefits of processing operators? We can combine this operator as needed. For example, if we need to convert coordinates, merge root node, and convert to S3m format, this operator can be combined into one processing operation, which is avoid the multiple input and output and improve performance as a whole. The second challenge is the object expression. How to manage a piece of surface data. As we know, that oblique data is unified data, which is cannot be squared because all entities are merged into one. However, with this monomer technique, we can embed vector data which contain the attribute of objects to our 3D oblique data, so that later query process will be carried on the vector data. But because it has been embedded with 3D oblique, it will look as if performing oblique data queries. In the past, singularization required the service to accompany the corresponding data sets. Now, we can draw directly on the front end, assign attribute, view in real time, and retain the result. This is another example of thematic map referring to the attribute of the buildings. We can separate by attribute and make a thematic by color, for example. Okay, the object information of real estate registration has spatial natures. The third dimensional information is only expressed in terms of attributes such as floor, height, and orientations. It does not accurately reflect the spatial location and scope of local entities. And it is difficult to determine the uniqueness of the spatial location of the property. With use of the 3D building to express the real space location of the object, we can use the 3D real estate table to express the mortgage and seizure information of the real estate unit, and combine the real estate table, household map, and attribute data to restore real estate registration information in all-around way. The next challenge is the effect repair. The first challenge is the effect repair for terrain. So, oblique photography model is a digital surface model that contains the real terrain informations. In the practical application, it is often necessary to impose the oblique photography model into a scene that has already a terrain information. Sometimes happen these two terrain data cover another. In order to solve this problem, we can replace or modify the original terrain to achieve the goal. But we don't want to modify the original data. We can use one of SuperMap iDesktop functionality, which is can modify terrain data in display level without actually modifying the original data. So as a picture shown here, on the left side, before the terrain modified, the terrain data covers the oblique photography model. After terrain is modified, the oblique photography level data is clearly displayed. The next challenge for effect repair is the flattened road. We can, in SuperMap iDesktop, we can use the texture replace function to replace some part of the terrain to make it look nicer as the picture shown. Next one is the effect repair for reject suspended object. We can remove the suspended solid from the oblique photogrammetry data. In SuperMap, this function called remove suspend solid in the OSGB processing group on the object operations. Next challenge is for the effect repair for tree. So the oblique photography is not very effective in the small scale object modeling, such as cars, street lamp, street tree, and so on. So this object often show broken. To solve this problem, SuperMap provide model flattening functions, which can remove the broken object, and we could place a new 3D model symbol in the original position to replace it. So this is demonstration of the matching of terrain and slope models using the TIN terrain mosaic function in SuperMaps. The next challenge is the effect repair for water surface. In the oblique photography model, there are some pore appear in water surfaces. That is because lack of data. SuperMap can restore the water surface effect of the water of this oblique photographic by filling a symbol of the water surface, and it is provide a variety water surface effect parameters such as reflection, calm water, rush water, and so on. Okay, let's move to other section, the integration between oblique photography and GIS. The first one is the data management. So the oblique photography model support richer spatial calculations and support 3D surface cutting, digging, inlaying, removing suspend objects, and so on. And this function support the GPU preview. And you can see the effect of the data processing before performing calculations. GPU preview means the calculation will be done by GPU to achieve faster performance. These are data operation functions that can be implemented to oblique photography, such as clip, mosaic, dig, removing suspended object, textural replacement, and others. In SuperMap, we can store the data historical through historical version data management, which is able to see the differences of the data time to time. Also, SuperMap able to transfer oblique photography coordinate systems. Okay, let's move to the 3D data analysis. As in these pictures, transportation is important link connection cities, as well as an important channel for urban development to transport people and logistics. A mountain road run through the mountain and shorten the distance between cities. But how to calculate the area of natural resource occupied by tunnel excavation? Since the tunnel and natural resource intersect in the 2D projections, the actual area occupied is not equal to the intersecting area. In 3D ways, the model of the mountain tunnel is established to realize the comparative analysis of 2 and 3D and provide accurate analysis result for the occupation of natural resources. We can also perform the 3D oblique spatial query to filter the data as shown as the picture. We can query by attribute or by spatials. There are many 3D analysis in SuperMap that can be performed to Oblique 3D model, such as the skyline analysis, sunset analysis, shadow red analysis, open analysis, and so on. For the skyline analysis is allow you to generate the boundary between the building tops and the sky from the observer. In this analysis is to set the high limit of solid objects. Okay. This is the same example. We can do a skyline analysis from 2D skyline to high limit the solid object of skyline. So the visual domain analysis in SuperMap is to analyze the collection of all the viewpoints in the area based on fixed horizontal angle of view, the vertical angle of view, and specify range radius relative to a certain observation point on the terrain or model data surface of the scene. The analysis result uses the green area to indicate that is visible at the observation point, and the red area indicate that is not visible at the observation point. So this is our spatial analysis result that can be performed to 3D solid object such as the visibility analysis, shadow analysis, skyline analysis, and others. At present, SuperMap can use the 3D terrain modeling result of elevation data and use the slope and aspect analysis function to provide a reference for the water and soil conservation planning of mountains, promote the sustainable use of water and soil resources, and maintain the natural ecological environments. At the same time, support the supervision of the mountain itself, avoid illegal land reclamation in some areas, and reduce the adverse impact on hydrology and the environments. This case took place in China because China has complex topography, high mountains and deep valleys, vertical and horizontal ravines, complex geological condition, and geological disaster are prone to occur. According to the 3D terrain modeling result of the elevation data, The slope analysis function can be used to quickly and comprehensively accurately find the risk point of geological disaster and provide a reference for decision making and supervision of water and soil conservation. Okay, let's move into the next session is the 3D simulations. So this is the example how flood analysis can be performed. The flood analysis based on surface data to create water flow simulations. Okay, this is another example using the voxel grid to achieve visualization of invisible continuous space data, such as communication signal strength. Other example of pollution field simulations. We can set these parameters. So let's move to the data output. SuperMap able to export into other data format from Oblique photography model, such as the digital surface model, DSM, digital line graph, GLG, the dome format, and also the street elevation format. Also, SuperMap support the output to STL file format, which is the file format used for 3D printing. This is how 3D printing works. First, it will load the STL format, and then we need to pass it to 3D printing equipment, and then 3D printing process, and we got the 3D printing result. Okay, let's move to the Oblique photography and Gis applications. This is one of examples. The system for urban planning that has some basic measurement function, such as measuring distance, measuring area, measuring the height of buildings, measuring the volume of building, and so on. Measuring the height and volume of a building can only be easily achieved in 3D system, but it cannot be done in 2D. This is another case. This is a case of planning and designing road and underground pipe networks directly on the 3D model of Shanghai City in cooperation with the Architectural Design Institute. This design is completely different from the previous product of the Architectural Institute. It is very intuitive and powerful. It provides the owner with a 3D design of product, and the feature application prospect of this method are also very broad. This is another example of application to show the model surface excavation integrated of ground and underground functionality. Another example, this is the application when 3D auxiliary planning system in use. We can put a 3D model here. Okay. So this is about the urban planning sample applications. We can compare several plans in the same environment and compare them in terms of apparent designs, floor area, greening. That is very intuitive. Okay, this is a new product we developed based on the 3D models and combined with the needs of the planning and construction department. In the system, the 3D model is superimposed with the general plan and detailed plan of the city. The planning and construction department can use this system to complete some tasks very conveniently. This is another different screenshot from the same applications. Actually, it showed the limit of the buildings. If the buildings height more than the limits, it will show like visualization, the red buildings. This is an interface for the operation of the 3D real estate information platform. If we click on any building, unit, or even any small house, the corresponding attribute in the database will be displayed. Also, we can do query. Okay, this is another case. This is a case of planning and design of road and underground pipe network directly on the 3D model of Shanghai City. Actually, the same with the previous application, just different screenshot. Another screenshot from the same applications about the planning and designing road and underground pipe networks directly in the 3D. Okay. After understanding the concept of how Oblique data will be displayed and processed on the SuperMap platform, now let's discuss what it will look like when integrated with other data. Basically, this Oblique data is useful for displaying the real world condition in more realistic way, including storing elevation informations, so that terrain can be seen from one point to another. Because of this, it will be very good if the Oblique model was integrated with a building plan model. That way, you can know what the condition will be when you wake up. As an example, for road design data, building dams, and so on. Besides that, it can also integrate it with other non-spatial data. For example, data from CCTV in the form area of monitoring video as follows. Also, it can be integrated with Street View that can be useful for navigation, as shown in this video. Okay, because this Oblique data is spatial data, we can also treat it like spatial data, such as transforming coordinates, georeference, translations, or combining it with other data. The following video is our successful integrations of BIM spatial data in CATIA format with oblique photogrammetry models, terrain models, and orthophotos. Okay. The question is how SuperMap can display 3D data for various data format and for various terminal. Here's the answer. Basically, as long as the data can be imported into the SuperMap platform, we can create the data format of S3m as follow. S3m is a 3D data tiling result format, and it is this format that will be brought to various terminal, not the raw data. We provide a free S3m data file reading and writing software development kit and provide development tool example, sample data, documentation, and so on. We also provide free data format conversion tools, including tilt photography model to S3m tools. Tilt photography data can be OSGB or XML with OBJ file format. Also the 3D tiles and S3m trick conversion tools. So let's move to the multi-terminal display. Multi-terminal display means that it can be displayed on various terminals. The flow is more or less like this. The data is initially only displayed on certain local operating system that can be Windows, iOS, Linux, and so on. And then it will be brought to a web browser terminal using the Chesium framework, whose implementation uses iClient 3D for WebGL. This process is done based on the JavaScript programming language and without using any plugin. The development process is quite easy and very easy to scale up to larger applications. The existence of this multi-terminal concept also support the development of richer applications. For example, being integrated with other data sources that can be provide information on the statistical condition of certain properties. And this is another example, the 3D data visualization in a web terminal developed by WebGL. We can give good effects such as night or day effect, light, and so on. This is other example, more applicable version to support smart city dashboard. We can put many, we call widget here, like the camera, the CCTV, and then the charting and others data. In addition to the browser, we can also open a mobile phone as a follow. In essence, as long as the file can be cached on the desktop, it means the SuperMap desktop, we can choose the type of cache for mobile so that our Oblique 3D data can be also in this and display on the mobile. This is another terminal for virtual reality. Yeah, as long as the raw data can be imported into the SuperMap platform, it can be also viewed as the virtual reality model. Besides the virtual reality, there is also augmented reality or AR, which is overlaying digital information with the real world. Here, not only the BIM data, but Oblique data can be also displayed as follow. The trigger in this case is a flat pane. So as long as there is a flat pane, it can be displayed as this video. Also, it supports the gesture. Okay. So in conclusion, the previous slide described the following sections of the diagram in this section on technology, interaction, and output. So here is the platform for the new 3D GIS technology system in SuperMaps. From the lower layer is the 2D and 3D data models, and then go to the multi-source of goes to into 2D and 3D integration technologies, and then goes to multi-source 3D data with the support of the data format, the OGDC and the S3m data format, and then the support for the various terminals. And lastly, we can develop a new 3D GIS application on top of it. Okay, and then we can move to the typical case. So as one of the 3D data types, oblique photogrammetry data support a wide variety of industries, good for smart city, planning, survey, agriculture, electricity, and so on. As long as the industry needs 3D data to help to visualize the real world in order to get better decision, then oblique photogrammetry can support it. And here is SuperMap acts as a bridge, as a liaison between oblique 3D data and other data to support problem solving in various industry. This is sorry. So this is the one-off video for tourism industry. On this video, there appears a 3D visualization of the hill that are displayed in really similar to the real world. There is an oblique data, which is a presentation of an area of 138 kilometer squares, which is produced 62,000 images. After the tiling, the result obtained were data with a smaller size, with size of 9.8 terabyte data. Okay. And then there is also a fire simulation. Sorry, I will. Okay, sorry. And then there is also for fire simulation. So far, fire simulation are possible only through textual and direct simulations, which will be time consuming and costly. But with the digital simulation, it will make the simulation easier. Moreover, it can be integrated with other data and business models. So this is another example for urban planning. This is to support the process of monitoring the progress of a building construction. For example, there is an area where the land use is to be changed. Then the surface change that occur are well documented with oblique data that is routinely acquired in that area. This is another example for smart community. Here's the implementation of the monomer will be very pronounced. As we know, that oblique data is unified data, which cannot be queried because all entities are merged into one. However, with this monomer, we can embed a vector data which contain the attribute of objects to our 3D oblique data, so that later the query process will be carried out on the vector data. But because it has been embedded with 3D oblique data, it will look as if performing oblique data queries. Basically, this oblique data is more to support the visualization of surroundings, which will often be combined with other 3D model data, which is design of the building to be built or also known as the building information model. So that in the end, it will be possible to obtain visualization if the building has already been built in a certain area. It is the same with the pipeline. You can make a schematic above ground visualized with 3D model, and also underground if there is a 3D pipeline model data. Another example for the water conservancy and electric power. Here we can use oblique data from the site that we have to support the analysis of determining the best pipe locations. Also for monitoring the condition of pipe or cables, and so on. I think that's all in these sessions. Thank you for your attentions. If you have any question, or I will leave next session to Olga. Olga, please.
Thank you, Mr. Ismail, for the interesting presentation. If you got any ideas or questions, please feel free to share with us in the Q&A session later. Now let's go into the second presentation of today. Nowadays, more and more people is experiencing the convenience of smartphones. It provides people the chance to work with internet and smart system with shortest paths. People can use smartphones to collect, upload, and access data from smart city systems. So under this circumstance, SuperMap has raised the idea about using AR and VR technology with smartphones to collect and visualize data. Now let's join Ms. Qin with her presentation, Mobile GIS, AR and VR technology and its application, to get more information on AR and VR usage in GIS. Let's welcome Ms. Qin.
Hello, everyone. Hello, everyone. Can you see my screen? Okay. Okay, good morning, everyone. This is Qin speaking. I'm a technical support engineer from Asia and Oceania Center. I'm glad to be here to have a chance to make a presentation for you. My presentation is about mobile GIS, AR, and VR technology and its application. Currently, AR and AI technologies are more and more widely used, and they have been integrated in many fields as well as GIS. So in the following contents, I'd like to talk about how SuperMap combines AR and VR technologies with geographic information. Here we have 4 aspects, contents here I divided into. Firstly, I'd like to talk about the AR, VR, and AI technology with SuperMap. Since in SuperMap, the AR and VR all combined with AI technology. So here I also want to talk about the AI technology. And then the next part is about the AI and AR in SuperMap and mobile. I'd like to introduce some applications with AI and AR. The third one is about the AR and the VR in SuperMap. And at last, I will introduce some practical application cases to make you better understand the content. So let's move to the first part. In this part, I'd like to talk about what is AR, what is VR, and what is AI, and what are their values. So let's firstly take a look at the definitions of AR, VR, and AI. Firstly, the AR, the AR is what we call augmented reality. It is a technology that calculates the positions and angles of a camera image in real time and adds the corresponding image. Then the next, the VR. The VR is an acronym for virtual reality. It is a simulated experience that can be similar to or completely different from the real world. And then let's take a look at what is AI. The AI is what we call artificial intelligence. It is a new technical science to research and develop theories, methods, technologies, and application systems used to simulate and extend human intelligence. We may know about the AR, VR, and AI more or less, but how does SuperMap apply? Here, I want to talk about how SuperMap apply with the AR, VR, and AI. From the AR side, we take AR core platform as the main and integrate with self-developed SRAM platform. And from the VR side, SuperMap combines VR with 3D technology, brings immersive 3D experience. And from the AI side, we take TensorFlow Lite and CAF2 platform as the main frameworks, integrate with OpenSieve and industry model to achieve deep optimization. And this have the proper features of mainstream from selection, and it is cutting edge technology supports, and our products is self-research technology integration. So with the AR and the AI, what we can get is that we can set correct positions of multiple graphs, display real texture of images. Moreover, the functions are integrated in a mobile application so that you can measuring, surveying, positioning anywhere and anytime. So as a self-research GIS platform, SuperMap integrates AR and AI into GIS, optimizes and reconstructs SRAM and AI technical framework. There has many achievements. So here let's see the AI and AR in SuperMap at mobile. These achievements are mainly reflected in mobile terminal products, including the two SDKs and a mobile app. SuperMap iMobile is a SDK for professional development, which can achieve mobile GIS development requirements. SuperMap iMobile Lite is a SDK for lightweight development, which is easy to complete basic GIS applications. And the SuperMap iTemplate is a mobile app developed by SuperMap iMobile. It integrates GIS functions including mapping, surveying, spatial analysis, navigation, and so on. In addition, the app has also combined with AR and AI, including some AR functions just like AR mapping, AR mirroring, and so on. So here, let's take a look at the main functions that provided in SuperMap. Here lists 4 functions according to GIS applications. The first one is object detection, and the second one is AR map, and the data collection, intelligent interaction, and the matching. Here I'd like to introduce these 4 main functions with AR and AI technology in details in the following slides. So let's firstly move to the first function, object detection. With the AR and AI, we can achieve object detection, and it includes these 5 main aspects. Firstly is about the video understanding, which can detect some complicated surfaces, such as the broken road or the manhole cover and others. And the second application is target detection. It can be used for detecting objects in the real world, such as this traffic lights detection. And the third one is target aggregation, which can be used for monitoring the traffic. And the fourth one is target tracking, which can track vehicles and record the tracks. The last one is license plate recognition, which can recognize the license plate, the car's color, and the category of the vehicle. So let's take a look at the video and understanding's application. Video understanding is a technology to classify objects in the video. It tells us what and where they are. And this video shows it recognizes the category as advertising and then records the operation. Then we can report it to some corresponding department. And this video is to recognize trash and also report this situation. Manhole cover recognizing, so we can get the classification results of the manhole. The next video target detection. Combined with GIS, we can not only just identify objects, but also locate to the map and record the information of objects. So that's very useful in surveying or city management fields. With target aggregation and statistics, we can monitor the traffic, compute traffic flow, and finally display the traffic conditions with the heat map. Through target tracking, we can monitor the specific vehicles and get their tracks. License plate recognition can recognize license plate, the car's color, and the category of a car. It can be used for recognizing and reporting the cars with broken rules in the field of traffic law enforcement. In addition, vehicle tracking can be used for multiple cars tracking. We can monitor the trajectory of selected vehicles, check the cars, check the car's status of each vehicle and check its route. So here we can check the running status of the cars. Then let's have a look at the applications of AI and AR used in AR map. Here lists 4 aspects. image recognition and placement, POI with navigation drop, and 3D scene, beam, notch, virtual science. Let's separately see how each application works. Through the recognition and extraction of image texture, we can put important information such as the interfaces, forms, maps, scenes, and POI into any actual scene in this space. So, and support various interactions, drag and drop, zoom in and zoom out. So as to enrich so as to enrich our enhanced real-world interaction scene, such as this video shows the Geographic Technology Conference, which we call it at GTC, is held by SuperMap every year. The video shows the detailed information and the schedule of GTC through AR image recognition. The next is POI recognition through AR. It is a position-based orientation recognition. We can use it to see what is in this area, such as what rooms are inside and what places are outside, and also marks on the scene. Then we can display 3D scenes through AR, such as topographic map, beam models, and 3D pipeline. We can display beam models with different scales, even the original scale. And also we can see the interior of buildings by interaction. Moreover, we can see the interior of the buildings with different angles and see each floors. What's more, also we can check the pipeline status and check the pipeline's attributes. And for the pipeline displaying, we can display the pipeline in the real positions in a real scale to help builders easily manage the pipeline facilities. Through the technical means of virtual SAM and IMU and sensor and position calibration, the virtual science can be added to the real map. This virtual science can be marked in the real scene, such as the route, location, and route to help you find where you are and where to go, and also you can check the related information you want to know. And this virtual science can guide you to the places where you want to go, also which can be used in shopping malls, museums and offices and other places. It can not only show the science I just mentioned, but also display the information you want to looking for. Based on indoor positioning, indoor geographic information data is projected onto the real scene. And you can directly see it in our far position facing the real scene. Then let's move to the intelligent data collecting. In this part, I'd like to introduce indoor positioning and navigation, intelligent mapping, and intelligent trunk connection, target recognition. Indoor positioning, let's see the video. While we are walking from inside to outside, we can accurately locate indoor and outdoor. And with virtual science, we can achieve indoor AR navigation, which can get you to go where you want to go easily. You can follow in the virtual science to get to your destination. And you can also achieve intelligent mapping. You can connect indoor data with AR method to help you make indoor mapping easily and quickly. You can also use the positioning connection to achieve the same purpose. Your chunk will be recorded as the connection data. This slide also shows collecting indoor data with chunk acquisition based on location, which can achieve the high precision. Then let's move to this part, intelligent interaction and mapping. With the previous video perception and acquisition, the results of this acquisition are further modeled to improve the original interaction mode and realize intelligent interaction, such as motion gesture tracking, gesture recognition, and intelligent voice control, also with AI figure captions. Let's say them separately. We can interact with map with motion gestures. Each gesture represents a different operation, such as zooming in and zooming out, dragging the map, and others. More than this, we can interact with maps with more gestures. Let's make the map view much more intelligent. In addition, intelligent voice control makes map interaction more convenient. You can operate map with voice control, such as inputting properties in the field surveying through voice control. And the properties can automatically fill in the forms. More than properties inputting, you can use voice control to open or close maps, open or close each layer, locate your location, or locate the position where you are searching, and also do the route plan, route navigation. All this can be achieved by the voice control. And AI figure compression can achieve map style setting automatically according to the image styles. So it will quickly give you a different styles map. Just to import the different styles of images. Moreover, we can not only access static virtual data, but also support to access video data to make the data live. The position and the chunks of various personnel and devices connected with real-time flow. Displayed on the dashboard with visualization, and IoT is responsible for interworking. So the first step is to detect the target according to the density aggregation. It is easy to detect and extract the peak and the valley vehicles due to road congestion and abnormal crowd aggregation. So this application can be used for the traffic flow monitoring. Then let's move to the third part, AR and VR in SuperMap. Here we also combine the newest virtual reality and augmented reality technology with GIS. Let's look at this example of VR. First of all, we integrated the data with multiple sources, including the BIM model, vector, point, and so on, to build this virtual 3D scene. Then, with the help of VR equipment to browse the scene, the view is accordingly changing when the viewer's head is turning up and down also. And by manipulating the handle to move forward or backward in this scene. This is the another video. So here we can see you changing this scene by turning up and down your head. And also to move forward by manipulating the handle. Furthermore, the viewer can also view the models underground by clicking the functional buttons and select a model object to view its attribute information. We can check the attributes of the 3D models by selecting the models. So then let's have a look for the real cases of the AR and the AI applications. According to the business classification requirements of urban government, the smart city project carries out in deep learning and training on dozens of abnormal conditions in urban areas, such as the garbage detection, broken road detection, which obtains target types that can directly identify specific categories, which can assist grid members in intelligent law enforcement and reporting. We used to record illegal vehicles by filling out forms manually. With AR application, we can easily and quickly scan cars and then get the car's information, including the car's license plate, the car's car color, and the position. After that, we can report the information by one click. So it's also easy to manage the cars and check the processing status. Let's look at municipal management. In the past, the information we could only see on tables and electronic maps can now be seen in the real scene through AR means. It makes geographic information look real and real time. We can use AR and AI in public safety as well. We can project the buildings to display the 3D building models, manage details of the buildings, such as the total households or total population, number of elderly, numbers of adolescents, and the details of the households. Moreover, we can display the interior of building to check the structure of the buildings. The indoor navigation can also be used for indoor emergency rescue. It can help rescue workers get the indoor location, plan the rescue route, and get to the destination by indoor navigation. With laser and SLAM technology integrated with deep camera and mobile camera, we can achieve scanning connections of buildings. The AR and AI can also be used in smart tourism. We can not only achieve the general functions such as scenic spot searching, route planning, 2D navigation, but also realize AR navigation, real-time position monitoring, real-time display of scenic spot information to give you a new appearance. Of course, the indoor and outdoor AR navigation can be used in multiple scenarios. This is what outdoor navigation looks like. The virtual signs are clear and real. So it makes you easily to find the destination. And this is indoor navigation, which can help you to find your destinations easily also, such as the tea rooms or toilet in the office. And it will show the room's attributes while you go through it. So then more SuperMap resources, you can find them in our official website, or scan the QR code to get more SuperMap products. Meanwhile, you can download SuperMap mobile application, SuperMap template from App Store of iOS systems or Google Play of Android system. So I think that's all for my presentation. Thank you for your listening. See you.